Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using KNIME. In this chapter we're going to talk about reduction via backward feature elimination. Now, backward feature elimination is a loop, and it's going to perform dimensional reduction against a particular machine learning algorithm. The concept behind backward feature elimination is really quite simple. At each iteration of the loop, using a selected classification algorithm, what might be a decision tree, a naive Bayes, etc., we're going to train on n number of input features or columns. Then we're going to remove one column at a time and retrain the model without that missing column. And then finally, the input whose feature removal produced the smallest increase in the error rate of the model, meaning its decline in accuracy, leaving us with n-1 input features. The classification, we then repeat this using n-2 features again. And then the feature who produces the smallest disruption in the classification performance is again removed, and this gives us n-2 features. The algorithm is going to continue until only one last feature is left for classification. Now, each iteration produces a model trained, therefore, on n to the k features and an error rate of e to k. Selecting the maximum tolerable error rate, we define the smallest number of features that are required to reach that classification performance. As you can imagine, if you look at this is an extremely CPU and time extensive process. This isn't something to be taken on lightly. And if you have many columns, and I'm talking about more than even a few dozen columns, this thing is going to run for a long, long time. So this is not a process you could run with, 250 columns in your model. The feature selection loop start actually launches a loop which performs the task I just described. It's going to train and apply the classification algorithm. In my case, I'm using a bag of models to find because I don't know which one is going to be the best. And then the end node is going to calculate the error rate for the implemented classification task and send back control to the start node, eliminating the feature which had the lowest decrease in error rate. And then the final list of input features and classification errors is produced as a model at the output of the end node. And then finally, the backward feature eliminator filter visualizes the number of features kept at each iteration and the corresponding error rate. And then the iterations are sorted by error rate. So you can either manually or automatically select the dimension reduction for the dataset yourself, depending on the level of error you want to tolerate. Often you're going to see that removing just a lot of input features can actually be beneficial in terms of classification performance, and at the same time the error rate increases or decreases very small. Looking at this example of donor data, for example, I can see the error rate on this training set only increases to around 0.02 when only a few input features are used, meaning all of those other features, though they might have a small enhancement to the model, they're going to make the model run much slower in the end. The biggest drawback to this function is the time it takes to execute it. And that's because the number of iterations is very high with dimensional data sets leading to very long computation times. Even a small example like we've been using, 230 or 250 input features in our data set, it produces an almost unusable execution time because it's got to eliminate one feature at a time, so it's got to remove 231 columns one at a time, and for each one execute the classification model, find the one that's slowest, and then remove it. Then go 230 times, and then 229 times. So basically, in this example, it would be 231 factorial. Therefore, it's really recommended that if you're going to try and use this as a dimensional reduction, you'd want to do it based on a second tier, meaning that you would have performed something like a missing values functional feature elimination, low variance, high correlation. Perhaps some of those would be done first and then consider doing backward feature elimination, because on a data set this size, it's just not feasible. All right, I have, with our sample data set, I've gone ahead and created a backward feature and forward feature elimination as a demonstration. But with 230 columns and 50,000 rows, there was no way this thing was going to run in days, literally. So what I've done is I've built a stratified sample, just 2,500 rows. And then I went ahead and applied a missing values feature that says every column, eliminate those with more than 30% missing values. And then I just randomly chose 50 columns with no specific reason. So the ROC curve here isn't the point. I wanted to simply provide you a sample of what the backward feature elimination might look like, so you could actually see its output and run. So as per usual, I always turn around and I do I set missing values. So I start by partitioning 80%, 20. And then I set missing values. Numeric are set to 0 and strings are set to unknown. And now this is the feature loop, the one part that we need to go through before we actually execute. So in the feature loop, we're using the feature loop selection. So I'm going to start here, and I've removed the target column is not in scope. And under feature selection strategy, I've selected backward feature elimination. And I have actually, in my case, said I have to have at least 10 features. You don't have to use this. It doesn't. You can let it fall. But since my data is kind of manually being played with just so I can allow execution times, I wanted to make sure there was a few columns left to actually look at. So that's backward feature elimination. Of course, you can do forward feature elimination, which is the next chapter, and you'll see it's literally the exact same workflow, changing this from backward to forward. So otherwise, I've left all the columns in play. And what I'm doing now, so within this loop, I've now got the end result was 11 columns. As you can see, the initial was 50 columns coming in. But after I ran it, it stopped at the 10 columns plus, which was my limit on the start node, plus 1 for the target. Now, as each loop passed through, I ran a decision tree. I simply took the data and I ran a decision tree learner and a decision tree predictor, and then I used the scoring node of the decision tree to get the model's accuracy. So in this case, it was 88% on the last node. And then the row filter, as you look at this one more time, there's the values for no, yes, and then the overall score. I want the overall score value. So the row filter, I did it based on including row ID, the overall row, and then the column filter, I just kept accuracy. So that's what got passed back from the feature decision tree, converted that to a table row, and then feature selection, I told it that I want to, by default it's maximize, but you could make it minimize. I want to maximize the accuracy column that's coming back. So let's look at the end loop and the result table. Okay. What I can see is when I started with the 50 features, the number of features and the model's accuracy. And then it tells me with each one, as I removed each feature, what happened to the accuracy. So it actually started at 86%, but look, once I started to drop these models down, I got up to 91% accurate by the time I had dropped the 57th. And it stayed pretty much in that area at 91%, but in fact it went and remained at 91% all the way down through 10, which means I can get rid of all of these features and still retain the accuracy level that I wanted. So the final feature selection filter is it gives me the option of basically saying for each one of them, the number of features, I selected feature automation based on score threshold. I said it has to be at least 90% accurate, and it chose the columns for me. I could have selected the features manually that I wanted to keep based on my review of the output. I could have reviewed it based on the best score. The best score was actually 18 features at 92%. And maybe that's what I want to do with this. So I'll go ahead and execute it. And then on my testing data set, I'm going to run the exact same using the reference column filter to make sure I get the same columns coming out. Now I can finish and execute my decision tree, and I've got the data now, the predicted value, whether this is going to be a yes or no. And if I drag this back, by the way, all the way over to the right, you can see what the original target was and what I predicted it was going to be. So no, I predicted no. No, I predicted no. No, I predicted yes. Yes, I predicted yes. So you can kind of see I'm getting some right and some wrong. And that's how we determine the features that come into this. Now, if I look at this in an ROC curve, the backward feature elimination, I'm sorry, I got too many variables here because I added a few. All I want is the yes values. I'm trying to, how often was I able to predict the yes target? And I've got two values, one for backward feature elimination, one for forward feature elimination. So I'm going to look at it again, and the blue line is my backward feature elimination. So again, looking at the ROC curve, this is the true positive rates. And then moving across this direction, okay, is the false positive rates, where I guessed wrong. And I can see that I'm not doing particularly well. Overall, the area under the curve is not great. Grand total, it's less than 55%. So even though the model's accuracy was 90%, the area under the curve is only 55%. This is not a good model. But of course, I made up the data, so that it's not shocking that I just randomly chose columns and removed them. This is just for note, this is the forward feature elimination, which you can see actually does a little better, but then begins to trail off and do worse. What's interesting is both of them eventually, the black line you see here in the ROC curve actually represents random guess instead of using the model. And both of them underperform random guessing as the false positive rate begins to increase. That, like I said, normally obviously you'd never start by stratifying your rows. You wouldn't just outright eliminate columns, or in my case randomly remove columns. But I did that simply so I could actually have the execution work and show you what the output would look like. That completes this chapter of the class. Feel free to move on to the next chapter.